In this video, we will look at designing to account for op-amp limitations. If we think back to our difference amplifier, we had a circuit to amplify the difference between two input voltages, and the gain value of that amplification was the resistor ratio R2 over R1. So ideally we would have liked to have just amplified the gain, but we also amplified the common mode voltage. And the ratio of the gain we wanted, the difference gain, compared to this common mode gain, was defined by our common mode rejection ratio, CMRR value, which is typically around 80 or so for op-amps. So what we'll now do is consider the following circuit. So in this circuit, we've got three op-amps. We've labelled as A1, A2 and A3. And we've got them configured with these resistors. This is known as an instrumentation amplifier. And the idea is it's going to amplify the difference between the two input voltages V1 and V2. So it's very similar to the difference amplifier, except it's going to have a lot better common mode rejection ratio associated with it. In order to work out the transfer function of this circuit, we're going to use the principle of superposition. So we're going to look at the gain due to one voltage input, and then look at the gain due to the other voltage input, and then add the two results together to get the final output. So firstly, we consider op-amp 1, and we consider that to have an input voltage, and we consider that to have an output voltage labelled Vout1. And what we're going to do is put a voltage V1 on the input, and we're going to earth the other input V2. So that's going to have a zero potential. So if we go back to our circuit, I'll just clean it up. We're going to consider this op-amp here. We're going to have a voltage out here. We're going to call it Vout1. We're going to have a voltage input V1 here, and we're going to set this other V2 input to be equal to 0. So if we do that, what we have got is a non-inverting amplifier arrangement. Now it doesn't look obvious looking at it like this, but if you consider this is an output, or this input V2 is 0, this op-amp is configured in negative feedback, so this is virtual 0, so this is a virtual earth here, so we'll call that virtual. And if you see this arrangement, we've got V1 going into this non-inverting terminal, and this output is configured to go through R2, R1 to, in this case, a virtual earth. So this arrangement we have here is identical to our non-inverting amplifier arrangement. So the transfer function for our non-inverting amplifier was given by this, and therefore the output Vout1 due to the input V1 is defined by this term here. What we can now do, so again, I'll clean the diagram up. We look at this, and now we will say this is earthed, and V2 is some voltage. Again, amplifier A2 is in negative feedback, so this is going to be a virtual V2 at this point. So we've got a virtual V2 voltage here going through resistor R1 to the inverting input, and this resistor R2 is in negative feedback arrangement. So if you look at this carefully, and this point is 0, this is effectively earthed. So if you look at this arrangement carefully for A1, this is our inverting amplifier arrangement. It's a bit of a different, or it looks a different geometry because we've drawn it upside down, But if you look at how all the components are connected, it's actually identical to our inverting amplifier arrangement. So if we have earthed V1 and have a voltage V2 which forms a virtual V2 as an input, then our output now from op amp 1, which is due to V2, is given by our transfer function for our inverting amplifier arrangement. So by the principle of superposition, so we said we're going to look at each voltage separately and then add the result together to give us our output. The output from op amp 1 is going to be our two terms added together, so we get this term and this term. So that is our output from op amp 1. We can do exactly the same argument for op amp 2. So now we can look at op amp 2, we can ground V2 and look at where V1, which is forming a virtual V1 here. Alternatively, we can set V2 to be, we can set V1 to be earthed and have a virtual earth at this point and see what the effect of V2 is. So it's exactly the same scenario, and we're going to get a V out 2 here and a corresponding equation for our V out 2. So our first two op amps are outputting a voltage corresponding to this. If you look at our third op amp, is this circuit here. So we've got two inputs. We've got V out 1 going into this circuit and V out 2 going into this circuit. And this circuit is our difference amplifier arrangement. So we know the transfer function of our difference amplifier. So our difference amplifier is just amplifying the difference of the input voltages, and because all of these resistors are the same value, R3, then the gain is going to be 1 in this case. So we've got a difference amplifier with a gain of 1. So our output, our ultimate output V out, is going to be the difference between V out 1 and V out 2. So our output voltage is going to be the difference between V out 1 and V out 2. So we're going to take away, we're going to have this value, take away that value, and if we work that out, we get this term here. So we have a difference amplifier where we're amplifying the difference of the original input signals with a gain term defined by these resistors. So it's similar to our other difference amplifier, except it's a slightly different transfer function. Because we've got a difference amplifier here, we're still going to have the same problem. We're going to get our common mode voltage gain on this. And our common mode voltage gain is the average of the input voltages, which is V out 1 plus V out 2 over 2. And this is going to give us a value for our common mode voltage gain, our common mode voltage term of this. So we've still got the same problem. We've still got an amplification of the difference, but we've also got an amplification of the common mode voltage. So in that scenario, we know different to the difference amplifier. The subtle difference in this case is that we have made the common mode voltage gain to be a constant value, where our difference gain is related to the values of the resistors. So we can control our difference gain by setting appropriate resistor values. And what that means is we can set this to be a very high gain while keeping this gain constant, and therefore we effectively increasing our common mode rejection ratio. So we haven't totally eliminated the common mode gain, but we have effectively reduced its effect because we've increased the common mode rejection ratio, and we can get common mode rejection ratios well in excess of 100 dB. So that's better than just the normal difference amplifier. We don't have to build these circuits. So we don't have to build that from 3 op-amps. They actually come pre-packaged as an individual chip. So for example, the AD620 is an instrumentation amplifier with, I believe, a common mode rejection ratio of about 120 dB. So if you want to amplify the difference between two signals, then rather than use a difference amplifier circuit, you would go for an instrumentation amplifier because you get better performance. So that is one way we can design around some of the limitations. By suitably designing a circuit, we can improve on the performance of what would be normally achievable. So to summarize today's videos, we've looked at op-amps, and if you consider the 2 golden rules, so that is in negative feedback, the output tries to make the input difference 0. And the second rule is the op-amp doesn't draw any current from the inputs. Then we can work out what the transfer functions are of a lot of different circuits. We can build up more complex circuits by just simply using these basic circuits as building blocks and combining several of these basic circuits to make a more complex circuit. So we'll look at doing that in tomorrow's circuit design session. Always consider actual performance of op-amps when you're actually building these things in practice. So as I said, this module, we won't be sort of pushing op-amps to the extremes that we need to worry about limitations in op-amp performance, but it's something that you should consider when you're designing your circuits.